Thank you. Thanks to all the organizers. Great pleasure for me to be here. I'll be talking about joint work I've done with Ludovic Stéphan, who's a student of mine at INRIA, and Don Towsley, who's a professor at UMass in CS. And so this work falls in the area of inference problems with planted structure. And I've listed three classical examples of such inference problems with planted structure. There's the community detection problem, the planted clique detection problem, the planted dense subgraph detection problem. All three have received a lot of attention. And typically in those kinds of problems, what you want to do is to either detect whether an observation has some planted structure within it or not. And second, assuming it does have such a planted structure within it, can you recover this planted structure? So these are the two things one is typically after when addressing those models. And there are recurring phenomena that have been observed, at least in the three examples I've been listing. There are those three very interesting phases that show up. There's the information theoretic impossible phase, where there's simply not enough information in the observation, so you cannot conduct the task that you're after. The hard phase, where it's information theoretically feasible to do the task, but there are no known polynomial time algorithms. And finally, the easy phase, where it's not only feasible, but it's known to be feasible in polynomial time. So that's one feature. And another interesting feature that is common to the three examples I've been listing is that the boundaries between those three phases tend to be common between the two tasks of detection and reconstruction. So these are phenomena that seem to be somewhat general. So the kind of problem we are looking at is motivated by a network security scenario that Don Towsley brought to us. So he's been into network security for a while, and so he asked the question, if you observe communication patterns between a number of agents, can you figure out whether some of them are actually doing something weird? So more formally, you may have a set of attackers. They may be planning something, and if they plot, then they would set up connections between them to arrange the scheme. And so they would set up such connections so that there's a tree of communications between them, so that information flows between all the attackers. So in that context, we would be interested in the detection task as before, which would be to say whether an attack is underway or not, given an observed graph of communications between agents. And second, if you have decided that indeed an attack is underway, then can you figure out who the culprits are? All right, so pictorially here is a tree of communications between attackers. These are the normal communications, and then you remove the colors, and you have to figure out who are the green guys in this graph. So to make progress on that, we'll look at a toy model, so very toy model, highly stylized. We'll assume normal communications follow patterns of a Erdős-Rényi random graph. So we'll have n agents, n being large, and then we'll fix the edge density, so the average degree to be roughly lambda, where lambda is a constant. So, and if an attack occurs, we would augment this normal graph by a tree among k nodes, and we pick the set of k nodes uniformly at random in this graph. So you can tell already that what I will be explaining to you will be of little use to either terrorists or counter-terrorism agencies, because we are somewhat remote from realistic communication patterns. But we'll have interesting findings from a theoretical point of view, nevertheless. Most of the talk will be focusing on the simplest possible tree you can imagine, which is a path. So a bit of notation. P naught will be the distribution of the graph without the attack, so that's the Erdős-Rényi random graph. P1 will be the distribution of the observed graph under attack. So for detection will be the task of distinguishing P node from P1, and to assess whether you are able to reconstruct the attack or not, we'll use this notion of an overlap. And so if we produce an estimate of a set of attackers, K hat, and if the actual set of attackers is K star, then the overlap is just the size of the intersection between your two sets. And we'll say we've succeeded completely in doing the reconstruction if the, so I would want to throw an expectation at that. So the expected overlap is K plus little o of K. We say it's partial if it's omega of K. Say I've successfully recovered 20% of the attackers. And we fail if we cannot do more than little o of K. Okay? So I spend most of my time discussing the phase diagram we could establish for this reconstruction and detection problem for path trees, and I'll finish with considerations of other trees. All right, so here's the left part of this phase diagram, which is expressed in terms of lambda, the density of the base graph, and in terms of K, which is the size of the attack set. And so this is the less surprising part of this phase diagram. When the lambda parameter is below 1, then we have a curve distinguishing between the feasibility and infeasibility of both detection and reconstruction. So basically, if the, for given lambda less than 1, if K is above log n over log 1 over lambda, then you can do reconstruction and detection easily in polynomial time, whereas if you are below that, you fail at both in an information theoretic sense. So no hard phase, and the same boundary for the transition between the impossible and the easy phase. The more interesting part of this phase diagram is when the graph is a bit denser. So when lambda is strictly larger than 1, we have a critical line at roughly K over the root n. And more precisely, what we see is that for K little o of root n, then detection is impossible, whereas it's easy when K is omega of root n. So we've got a clear transition here. But the interesting feature is that this is not the boundary for the reconstruction task. And we find in this problem that reconstruction remains impossible so long as K is little o of n. So we've got this whole range of parameters where K is really large, you can detect, but you cannot reconstruct. So now I'll spend some time explaining how we reason to establish those things about these 4 regions in this phase diagram, starting with the upper left. So when things are feasible and the graph is sparse, lambda less than 1. If you pick K larger than this critical value log n over log 1 over lambda, you may identify the longest path in your Erdős-Rényi graph, and so without an attack. And so you may find the longest path in your observed graph by running a bunch of depth first searches. So this is something you can get at algorithmically, and you can analyze how it scales without the attack. Without the attack, the probability that your largest path will exceed K is little of 1. And this is something you can show by the first moment method. So this is a simple exercise. So that settles the detection problems. So if you find a path that is larger than K, then you can safely decide that an attack is underway. Otherwise, you can say no attack is underway. So to do a reconstruction now, what you would do is to identify in your graph the connected component that contains the attack path. So this longest path you found. And so how would that look like in this model? You would have the attack path like that of length K, and then you would have small dangling trees like that. So that's the typical behavior for this connected component. And so peeling is the operation which consists of removing degree 1 nodes. And so a tiny tree like that, if you apply peeling recursively several times, it will vanish. And so if you do that, say, square root of k times, maybe you'll eat up a little bit of the extremities of the attack path, but this will be a negligible fraction. So the result of the peeling operation will produce an estimate that has overlap k plus little of k, so you will succeed. So that addresses the simple upper left part of the phase diagram. And now I'll move to the bottom right part of the diagram. So it's not the natural order, but anyhow. So how do we argue about undetectability? The fact that it's not possible to detect when k is little o of square root n and lambda is larger than 1. So we play with the likelihood ratio between the two distributions. And so this is something you can express very easily. The likelihood ratio is given in that case as something that's proportional to the number of k-length paths in the observed graph divided by the number of such paths in the complete graph, and then you have to multiply by the 1 over the probability that a particular such path is present in the Erdős-Rényi graph. So this is an explicit formula, and based on that, you can work on the statistics of the likelihood ratio. In particular, you can analyze its second moment under the Bayes distribution p-naught. And so a convenient expression for that is that the second moment of your likelihood ratio is the expectation of n over lambda times the number of common edges between a fixed k path and a randomly picked k path. So this is something that can be seen in a couple of lines. And so you can write explicit formulas for that involving lots of combinatorial terms, but it's quite messy. And so to really understand the behavior of this quantity, we came up with a bounding Markov chain argument. Basically, we want to, so that's the quantity we want to show is close to 1. If we show this is close to 1, we'll have nice properties and we'll be able to conclude. And so the way we proceed is we produce a Markov chain which basically represents as you construct your random path, whether you're outside the fixed path or you just hit the fixed path or you've hit it the previous time and you hit it once again, in which case there is a common edge. So that's a very simple Markov chain, and we can show that the quantity we are interested in is upper bounded by the expectation of this thing n over lambda times a sum of functions of the states of this Markov chain. And so now we're in good shape. We can compute that explicitly. And this will be given by some power of a matrix that is related to the transition probabilities in the Markov chain. And it's going to be a matrix that is a fixed matrix plus k over n times another fixed matrix. And so when we raise that to the power k, we can use perturbation arguments, and we can establish this kind of a bound on this quantity. So it's going to be of order at most e to the k squared over n. So this will give us what we need, because if k squared is small compared to n, then the second moment of the likelihood ratio is going to be 1 plus little of 1. And so this gives us bounds on the total variation distance between the two distributions. So this addresses the infeasibility of detection in the bottom right of the phase diagram. This is actually the same kind of analysis relying on a bounding Markov chain argument that works for the bottom left. And so we have that detection is impossible in the bottom part of the diagram. It turns out that in general, it's not true that you can right away say, if I cannot detect, then there's no hope, I can reconstruct. There's a counterexample, I believe, in a paper by Jamming and co-authors, that this implication is not true in general, but it turns out that in our setup, if the second moment of the likelihood ratio is 1 plus little of 1, indeed reconstruction is impossible. So we get the picture we wanted for the bottom part of the phase diagram. So we're left with addressing what's happening in the upper right of the phase diagram, where detection is feasible but reconstruction is not. And so what do we have first? The argument for detectability. So if you knew the lambda parameter and you observe an Erdős-Schrödinger random graph with lambda n edge over 2, perhaps lambda n over 2 edges, plus order square root of n edges, and if you add k additional edges where k is large compared to root n, just applying a threshold to the count of edges would reveal the fact that an attack is underway. But you even have more than that, because this would rely on knowledge of lambda. If you don't know lambda and you're given the Erdős-Schrödinger graph plus this long path, you can consistently estimate lambda and k and discriminate. And in fact, to do that, you would need to count the number of isolated components, the number of isolated edges, number of isolated components comprising isolated nodes, isolated edges, and isolated components comprising 3 nodes. Massaging that, you get your estimates, and you can distinguish, and you don't need to rely on knowledge of lambda. So in other words, if you add a path of length large compared to root n to an Erdős-Schrödinger graph, you mess up the local structure and you mess up the counts of the small connected components, and you can see that. So that's why detection is doable in that range. So the more interesting, perhaps, argument is the one that remains, which is about impossibility of reconstruction that I'm going to try and convey now. Because of our metric for measuring the accuracy of reconstruction, we know the best algorithm there is. It's going to be maximum a posteriori. So to achieve maximum overlap, we'll just construct our set k hat by including the nodes which are crossed by the largest number of k paths in our graph. This is exactly what maximum a posteriori in this context does. And so here's the argument we have to put forward to show that reconstruction is impossible in this upper right corner. So given the planted path, we can consider alternative segments for a portion of this planted path. And so in our graph, we may consider all the alternative paths of a given length. So I may have I may have a range for the start of this alternative path, another range for the endpoint, and I can consider all possible, alternative paths. And so what we are going to do is to pick uniformly at random from the graph such a green alternative path. And what we can show next is that the distribution of the graph conditional on having planted the blue graph and having sampled the green alternative segment is in total variation close to the distribution of the graph if we had planted the blue and the green. And so in other words, the alternative segment is indistinguishable from the true one. So this is a lure that maximum a posteriori will consider as good as the true segment. So if you do that and move around your alternative segment, your lure, you can show that the overlap you can achieve, the optimal overlap, can be at best k over 2. And by the way, I'm skipping a lot of details, but the bound on the total variation distance holds because we can show that the number of alternative segments we can consider concentrates around its mean. This shows up when you try to unroll the argument. So we have a bound of k over 2, but actually we can push that. And this is what we do, in fact. So the construction is very hairy in the end. There's a lot of technicalities, but essentially we chop the path into shorter segments, and for each of them we construct not just one lure but T such lures, and so we can show that for we can show the same kind of proximity in total variation between P1 and having planted blue and green segments, and so overlap has to be at best K over T, and we can push T to be as large as we want. So the overlap has to be little of K. All right, and the reason why we want to chop this into sub-segments is that we need to show concentration of the number of candidate green paths, and if we try to do it right away for the whole segment, it turns out that the number of length K paths does not concentrate in those Erdős-Rényi graphs. We don't know how it behaves. It simply does not concentrate with the tools we have. We cannot show that. So this is why we chop into smaller segments, and that adds a bit of technicality to the argument. All right, so what can we say about other trees? So another tree which is very straightforward to analyze is the star. So if, taking the viewpoint of the terrorists, what is the best tree they should use? Well, if they want to hide in a graph with the smallest possible lambda, then maybe a star is a bad idea and a path is a better idea, because if lambda is larger than 1, they can hide as many as square root of n individuals, whereas for a star organization where everyone reports to the boss, then you can hide logarithmically many agents. And this is very easy to establish. You can show concentration of the number of nodes of high degree, or this is again a first order method which gives you everything you want. And so this is a case which is easy to address. But the other one on which we can say a few things is D trees. So these are trees where starting from a root you have D children, and you keep iterating that over generations. And so the star is a D tree with D equals K minus 1. The path is a D tree with K equals 1. And in between, we can say a few things. So the picture seems to look like the one we had for planted paths, but it's less complete. It's harder to analyze. We don't have the equivalent of the Markov chain bounding technique for this. But here's what we have. So there is again a dichotomy between dense graphs and sparser graphs. The cutoff being not at lambda equals 1, but at lambda which depends on D, and which is actually precisely the threshold for the apparition of what's known as the D core in Erdős-Rényi random graph. So you can parse that. This is the smallest lambda such that there is a positive root P to the equation P equals the probability that Poisson of lambda P parameter random variable exceeds D. Okay. And so what do we know? Below this lambda D is where we can say the most. And so here we can identify a critical depth for those trees, H star, which is log n over log D, below which both detection and reconstruction are impossible, and above which detection is easy. You can find such trees of depth which is larger than what you would have without the attack. So just recursively looking for such trees, you can find them. And a distinct feature compared to the path scenario is that you can never hope to reconstruct everything in those cases, because you have uncertainties about the leaves of the trees. So you can at best achieve an overlap that is order K but not K. And so on the right-hand side, we have again, the same argument for detectability when k is above root n, so the counts of small connected components are messed up and we can detect. We know that at best we will have uncertainties about the leaves of the trees of attackers, so overlap of k is not going to be possible, but we are missing what we believe should be the case, that reconstruction is again impossible, and we would at best get overlap over the little o of k. Yes, we don't have, for k equals little o of root n, we don't have the analog of the Markov chain bounding argument, hence the question mark. All right, so I might have been too fast, but that's probably okay. So I'm reaching my conclusion slide. So the takeaway messages are to me are the following. Initially, I was interested in this problem, thinking this is going to be yet another example of this trichotomy with a hard phase between the easy and the impossible phase, and this will help us understand what triggers those hard phases. And we did not find any such hard phases, at least at the resolution we took. Maybe by doing a finer analysis, we may identify some hard region, but not at this stage we have not identified this. However, the other interesting phenomenon we found instead was the fact that the boundaries between the phases differ from reconstruction to detection. So this is something that in retrospect is quite natural. Reconstruction is hard in those cases because there are many copies of the planted structure present in the environment you're dealing with. So I guess this is the simple explanation. However, to unroll the argument, we need to show some kinds of concentration properties for these numbers of copies of the structure of interest. And I guess, I mean, there are all kinds of variations on these problems you may want to look at, and if you want to be relevant to terrorists or to the NSA, and even in this simple case of an Erdős-Renyi background graph, we have not totally cracked the problem. We don't have the full phase diagram for irregular trees. We could plant trees that are more branching process-generated trees, and what are the benefits of that? Maybe it's harder to identify nodes from those trees. So there are a couple of questions we could imagine along that, and so we did not make progress on what triggers hard phases, but here's the case where we don't see them. Okay. With this, thanks.
For example, you had the line, which has sort of very thin leaves, and then sort of you took the regular trees, which have like sort of it's effectively expanding. So clearly, there are sort of if trees were, let's say, geometrically growing, would that change your phase diagram? So not just line, but let's say I've got sort of higher degree trees, but sort of the boundary of the trees is growing polynomially rather than exponentially.
Where would you put the boundary between dense and sparse?
No, so for example, you had that so before, yes. So for example, here in the my left hand side, the recovery part would sort of mean that sort of if you did peeling, potentially your boundary that you're going to eat up where uncertainties will be small of the total number of things.
Okay.
And hence potentially your reconstruction result would be different. Would that be true?
I would think so, yes. I guess what we would need to look at is how we identify the tree. So for the regular D tree case, you can really look for D trees of depth 1, and based on that, look for D trees of depth 2, and you can do that recursively. So we would need to adapt that, but I would imagine this can be done if you have varying degrees as you move down the tree. in which case, yes, you could imagine you can have full recovery. Or maybe you could say even in those trees, maybe we can, with certainty, identify the root of the tree, or we have decreasing certainty as we move down, or maybe I'm not sure, but maybe you could be able to identify everyone but the last layer in those cases. So.
And then another natural model could be that sort of, well, you've got this Edo-Shirani graph with degree p, or sorry, lambda over n. But let's say the things that I'm hiding is lambda prime. But lambda prime is different from lambda.
So you're adding a
tree growing with sort of, let's say, a poison tree.
Right.
Would that sort of change things drastically from your, let's say, regular tree analysis?
We have not tried very hard, but you see we get stuck early on. Intuitively, it seems like it's the best tree to hide. I mean, branching process based with a poisson of spring seems it will look natural, and so you will confuse the detection mechanism or the reconstruction mechanism the most. But this is, I guess, what we could try to identify is, in this case, where does the shift from sparse to dense occur, and maybe we lower considerably the critical lambda in that case, still having low diameter trees. So that's a possibility, but yeah, this is a guess at this stage. So I mean, definitely this is a caricatural model, the Edo-Shirani one, and if we move to power law random graphs, things will be very different. And I guess, yeah, it's. I think there's value in doing that, both from the theoretical point of view and from the practical one. I mean. Although I don't know what would be the perfect scenario. So I took that from Don Tousley, the initial motivation, and then we did not think too hard about the applicability. But indeed, I guess there would be a mapping between the background graph you consider and the good structures you can easily hide in there. And stars would, for instance, be much easier in power law random graphs where you have tons of them. Yes, so that's, yeah, I don't know if I've answered your question, but. Okay. Okay.
So it's very applicable. Yes, very applicable.
All right. Good. Excellent.
Even less practically relevant question. So, is there any version of this question that is natural for the random regular graphs? Because obviously, I cannot plant anything with this regularity, but maybe I can plant it first something and then build a regular graph on top of it by configuration model. But because it contains random regular graph contains TSP, then maybe paths are not. I don't know if you've thought about this.
I have not thought at all about it. I guess the argument for detectability about messing up the number of small connected components, this would be no longer be the case. So it may be much harder to detect, I guess. So that's, yeah, I did not think about it, but indeed this would make for a different phase diagram, definitely.
So in the top part of the phase diagram, do you think partial reconstruction is possible or impossible?
For this one, I would bet it's as bad as for the line. So, but yeah, I would not bet much, but a little.